You and I are taught to think of weather as chaos. One day it is scorching, the next it is cold and grey, and it feels like there is no reason beyond random chance. Storms roll in, floods arrive, heat waves settle over cities, and we shrug and call it bad luck. Yet when scientists step back from the window and look not at days but at centuries and millions of years, a different picture appears. In ice, in rock, in tree rings, they keep finding the same strange thing. Beneath the noise is a rhythm, heat and cold, flood and drought, rise and fall of seas, all pulsing in patterns. The unsettling question is simple. Are we still moving with that ancient rhythm, or have we slipped out of its grip in a way no civilization ever has? And how would we even know? Think about your own memory of weather. You remember the summer that never seemed to end, the winter that locked roads in ice, the year the river nearly climbed into your house. Our brains are very good at holding on to vivid stories and very bad at tracking slow background changes. Your life experience is a few decades long. Earth has been running its climate experiment for more than 4 billion years. That gap in timescale is the crack that confusion slips through. What feels like crazy extremes to us might be nothing more than a small shiver in a very big system. At the same time, what feels normal because it has been true for your entire life could be wildly abnormal on a geological timeline. This is why climate arguments often talk past each other. One person points to a single cold winter and laughs at global warming. Another points to global temperature records and sees a planet screaming. They are not looking at the same clock. To understand whether our world is collapsing into chaos or following deep hidden rules, we have to separate weather from climate. Weather is the mood of the atmosphere right now, the passing thoughts and impulses that change hour by hour. Climate is the personality that emerges when you average those moods over years and centuries. If weather is a single note, climate is the melody played over the whole song. If you only listen for a few seconds, you will never know what the piece is trying to say. Climate scientists like to say that one hot day proves nothing, but a long string of hotter years begins to tell a story. That story is not written in ink. It is written in ice layers, in the chemistry of tiny shells on the ocean floor, in the width of ancient tree rings that live through long summers or crushing droughts. Each layer and ring and shell is a diary entry from a world that no one saw. Together, they tell us when ice sheets grew and shrank, when deserts marched, when oceans warmed or cooled. When researchers drill deep into the ice of Antarctica or Greenland, they are not just collecting frozen water. They are collecting trapped bubbles of air from hundreds of thousands of years ago. Inside those bubbles is the atmosphere of ancient Earth. They can measure how much carbon dioxide it contained, how much methane, how warm the planet likely was. They can line up those records with layers of rock on the ocean floor that track the temperature of seawater when microscopic organisms built their chalky shells. When those different records are lined up, a startling pattern jumps out. Earth does not drift randomly between warm and cold. It swings. It swings into ice ages and back out of them, over and over. Ice sheets spread over continents, crush mountains, then melt away and retreat. Sea levels fall to expose land bridges, then rise to drown low coastal plains. These swings are not evenly spaced like the tick of a simple clock, yet they cluster in regular bands of time that are very hard to ignore. A Serbian mathematician named Milankovitch spent years of his life trying to understand why these swings happen. Long before we had satellites or sophisticated computers, he sat with paper and equations and calculated how Earth moves around the Sun. The planet does not orbit in a perfect circle. Its path stretches and relaxes over tens of thousands of years. Its axis tilts more, then less. Its spin wobbles like a slowing top. Milankovitch wondered what those subtle changes in geometry might do to climate. He realised that if you change the way sunlight falls on Earth, especially in high northern latitudes, you change the balance between melting and freezing. It is not the cold of winter that controls the growth of ice sheets. It is the softness of summer. If summers in the far north are just a little less intense for many thousands of years, snow that falls in winter does not fully melt. It piles up, compresses into ice, and slowly crawls outward. That fresh ice reflects more sunlight back into space, which cools the planet even more. This is the start of a feedback loop. A faint tweak to the way Earth orbits the Sun makes summers milder in some places. Mild summers let snow survive, which grows ice. More ice reflects more sunlight, which cools the air and ocean, which grows even more ice. Over many thousands of years, that loop can tip the planet into a deep freeze. When the orbital configuration shifts again and summers grow stronger, the loop runs in reverse. Ice melts, dark land and ocean absorb more heat, and Earth warms. For a long time, Milankovitch cycles sounded like an elegant idea chasing proof. The real test came when scientists had long continuous records of past climate to compare with his calculations. When they did, they found that major ice age cycles lined up with the timing of changes in Earth's orbit and tilt with almost eerie precision. The temperature of the planet, reflected in chemical signatures inside ancient shells, rose and fell in step with slow changes in the way sunlight was distributed. This is one of the strongest hints that climate is not a runaway, uncontrollable beast. It is sensitive but structured. Small, steady nudges, applied over long times, can steer the whole system.
That also means it is possible to end up on a very different track if the nudges point in a new direction. Today, the geometry of Earth's orbit suggests we should be very slowly cooling. By the natural schedule, the current warm interglacial period ought to be easing toward the beginnings of another long winter. Instead, every major line of evidence says the opposite is happening. Global average temperatures have climbed rapidly over the last century and a bit, far faster than the slow orbital cycles can explain. Ice sheets in Greenland and Antarctica are losing mass. Glaciers in mountain ranges are retreating. Sea levels are rising as warmer water expands and added meltwater flows into the oceans.
The greenhouse gases measured in modern air have spiked to levels not seen in hundreds of thousands of years of ice core records. You might ask a fair question here. If climate has always changed, if ice ages have come and gone without any help from humans at all, why should we care that it is changing now? Maybe this is simply another swing of the same old pendulum. Maybe our measurements just happened to catch the system at a moment when it was already headed upward. This is where those ancient diaries in ice and rock become vital. They do not just show that climate changed, they show how fast it changed and under what kind of push. When we overlay the past century on the deep time record, it looks like a spike.
Most natural shifts between colder and warmer states in the recent geological history take thousands of years. In comparison, our modern warming sprint has unfolded in little more than 100. Imagine a dimmer switch that has always been turned slowly over hours, and suddenly someone jerks it to full brightness in seconds. The light is the same, but the way you reach it matters for everything that depends on it. The hidden clockwork of Earth is not just in its orbit. It is also in the way oceans breathe heat in and out, in the way winds wrap around the planet, in the way the sun's activity rises and falls. Each of these cycles has its own tempo, its own favourite timescale. Some are so slow that they rewrite coastlines and carve new valleys. Others are so quick that they can flip a season from gentle to brutal. When they line up, they can reinforce each other and produce extremes far beyond what any single cycle could do alone. To make sense of our present, we need to learn the language of those cycles. The long, slow orbital dance that sculpts ice ages. The multi-year mood swings of the Pacific Ocean that decide whether rain will nourish crops or drown them. The high-altitude rivers of air that keep polar cold locked in place until they suddenly fail. The shifting strength of Earth's magnetic shield that controls how much cosmic radiation brushes past the atmosphere. The pulses of the sun itself, which send waves of charged particles our way.
This can sound overwhelming at first, like trying to listen to a dozen songs at once and somehow hear the tune that matters. But we do not need to become experts in orbital mechanics or fluid dynamics to grasp the basics. We just need a clear map. When you know that some cycles control the background setting of the planet, while others provide sudden shocks, you can start to see why some years feel so strange, and why some decades become turning points in history. There is also a deeper, more personal reason to care about this hidden clockwork. Civilizations rise and fall not only because of politics and culture, but because of the physical stage they stand on. A long string of good harvests under a stable climate can feed art and science and exploration.
A series of failed monsoons or decades of unusual cold can topple empires. When we say that climate is the average of weather, we are also saying it is the average of opportunity and risk that every generation inherits. Today, we live at a moment when two forces are colliding. On one side are the ancient cycles that have always shaped Earth's climate. On the other side is the new human-driven push, created by burning fossil fuels, clearing forests, and changing how land and water reflect sunlight. One moves on the scale of tens of thousands of years, the other moves on the scale of a single lifetime. Their collision is the central drama of our age, even if most of us only feel it as a few more hot days each summer. If you have ever looked at a headline about record heat, or an unprecedented storm, and wondered whether it really proves anything, you are already standing at the edge of that collision. Our instincts are tuned for local patterns and short memories. Our tools are now powerful enough to give us a planetary view, but that view can feel abstract, detached from daily life. Part of our task is to build a bridge between those scales, so that a graph of temperature anomalies becomes as emotionally real as a cracked riverbank. One of the most effective ways to do that is to follow stories that unfold over different lengths of time. The slow story of ice ages written in rock and ice. The medium story of ocean cycles and wind patterns, written in harvests and storm tracks. The fast story of a single sprawling heat dome or atmospheric river event, written in hospital visits and flooded streets. As you move between these stories, patterns that once looked like noise begin to line up in a way that is hard to unsee. You can try a simple exercise in your own mind. Think of the most extreme weather event you have personally lived through. A storm, a flood, a wildfire, a heat wave that left you stunned. Now imagine that event as a point on a graph, one dot among millions of other dots from millions of other lives. Alone, it is a story. Together with all the other dots, it becomes data. The question that haunts scientists is not whether your dot exists. It is whether dots like it are becoming more common, more intense, clustered in new places. When we ask whether Earth has a hidden clockwork, what we really want to know is whether that increase in intense events is just the cycles flexing, or a sign that a new force has seized the gears. If the orbital rhythms and ocean patterns and solar pulses can explain what we see, then maybe we're simply passengers on a long ride. If they cannot, and the only way to match the data is to add the influence of greenhouse gases and land use changes, then we're no longer just passengers. We are drivers who have been steering with our eyes mostly closed. At the same time, it is too easy to fall into a story where nature is static and humans are the only source of change. That is not true either. The ancient cycles have not stopped.
The next slow dips and rises in orbital forcing are already baked into the future. The oceans will keep sloshing heat back and forth between surface and depths. The winds will still snake around the globe in bands and rivers. The sun will keep breathing in an 11-year rhythm. If we want to understand our moment, we have to see how our actions stack on top of everything the planet was already doing. So as we move forward, we will not simply declare that climate change is real and end the conversation. We will test that idea against the best evidence we have. We will see how well the hidden cycles lined up with past shifts, and how much of the recent spike they can honestly account for. We will follow the threads of orbital mechanics, deep ocean currents, atmospheric circulation, shifting magnetic fields, and solar moods, and ask where each thread still holds and where it snaps. Only then can we answer the question that opened this journey in a way that feels earned. Are today's extremes just another verse in a very old song? Or has something genuinely new entered the chorus? To even attempt that answer, we need to step inside the first of Earth's great rhythms and feel how a barely noticeable change in the way sunlight falls can, over time, freeze and thaw a world. If you picture Earth from far away, not as a place with cities and clouds, but as a moving object in space. The first thing you notice is its path. It circles the Sun over and over with reliable regularity. At first glance, that orbit looks like a perfect circle. For a long time, people assumed it was. Yet when you look closer, you find that our path is actually a stretched loop, slightly squashed into an oval. Over tens of thousands of years, that oval grows a little more round, then a little more stretched, in a slow rhythm. This changing shape is one of the quiet gears in the clockwork that Milankovitch was trying to understand. He called this shape change eccentricity. When the orbit is closer to circular, the distance between Earth and the Sun changes only a little during the year. When the orbit is more stretched, that distance swings more. Because of this, the amount of sunlight we receive at different times of year shifts slightly. On paper, those shifts look tiny, only a few % difference in energy at certain latitudes and seasons. It is hard to imagine something so small doing anything dramatic. Yet the climate record says it does, especially when that change joins forces with other slow motions of the planet. The second motion is the tilt of Earth's axis. The planet does not spin upright, it leans. Right now, that lean is about 23.5 degrees. Over roughly 41,000 years, that tilt rocks back and forth between a little more and a little less. When the tilt is greater, seasons are more extreme. Summers are hotter, winters are colder, especially away from the equator. When the tilt is smaller, seasons are milder. The sun's rays stay more evenly spread between summer and winter. The third motion is a wobble in the direction that axis points. If you have ever spun a toy top and watched it start to circle as it slows down, you have seen something similar. Earth's spin axis traces a slow circle in space over about 23,000 years. Right now, the North Pole points roughly toward a star we call Polaris. Thousands of years from now, it will point somewhere else entirely. This wobble does not change how much sunlight Earth as a whole receives, but it does change which hemisphere leans toward the Sun during different parts of our slightly stretched orbit. Eccentricity, tilt, and wobble act together like three overlapping rhythms. Each one on its own would gently shift the distribution of sunlight across latitudes and seasons. Combined, they create patterns of stronger or softer summer sun at high northern latitudes where massive ice sheets can grow. Milankovitch reasoned that these patterns should leave fingerprints in the timing of ice ages. Stronger summer sun would tend to melt back ice. Weaker summer sun would tend to preserve it. Here is the twist that often surprises people. It is not the cold of winter that matters most for building an ice age. It is the warmth of summer. No matter how brutal the winter is, if summer comes roaring back with intense sunlight, most of the snow will melt. The ground resets. Ice cannot build up year after year. But if summers are just moderately cooler for many thousands of years, snow begins to survive. It lingers as patches, then fields, then thick layers. Under its own weight, that snow compresses into ice. Ice has a very different personality than bare rock or soil. Fresh snow reflects most of the sunlight that hits it. Where a dark forest or ocean would drink in that energy and warm up, a snowfield throws much of it back to space. This is the ice albedo feedback. Add a little more snow, reflect a little more light, cool the surface a bit more, which allows even more snow to survive. Slowly, a patch of bright white creeps outward and thickens. Over tens of thousands of years, it can grow into a continental-scale ice sheet that is kilometers thick.
Now imagine that process running in reverse. When orbital changes line up to give high northern latitude stronger summers, ice begins to melt back. As the white cover shrinks, darker land and water are exposed. They soak up more sunlight, warming the air and ocean. That extra warmth accelerates melting. In both directions, this feedback magnifies the original nudge from the changing orbit. A small change in sunlight distribution becomes a large swing in planetary climate over time. For decades, the Milankovitch idea was a puzzle piece looking for its missing neighbours. Then ocean drilling projects pulled long cores of mud from the seafloor, and those cores turned out to be time machines. Layer by layer, they held the shells of tiny plankton that once floated in surface waters.
The chemistry of those shells recorded the temperature of the water in which they grew. When scientists measured those shells and stacked the data, they saw a clear, repeating signal. Peaks and valleys in global temperature lined up with the predicted timing of orbital cycles. The match was not perfect, but it was far too close to dismiss. Roughly every 100,000 years in the last few million years, major glaciations waxed and waned in step with the slow stretching and relaxing of Earth's orbit, shaped by the tilt and wobble on top. Other climate records, like gases trapped in ice cores, echoed the same rhythm. Carbon dioxide tended to be lower during deep glacial periods and higher during warm interglacial periods, amplifying the cooling and warming as the system swung. You can think of this as Earth breathing very slowly. Inhale ice, exhale warmth. Each breath takes tens of thousands of years. During the cold inhalations, ice caps expand, sea level drops, dust storms become more common, ecosystems shift toward hardy grasses and shrubs. During the warm exhalations, like the one we live in now, ice pulls back, seas rise, forests and wetlands reclaim territory. Human civilization sprouted during one of these warm pauses, a stretch of relative stability between major glaciations. Here is where the story becomes personal. If we track the current state of those orbital cycles, the coming thousands of years should lean gently toward another cooling phase.
The exact timing and depth of that future ice age are complicated and still debated, but the basic trend is clear. Without any human influence, the slow background forces should be nudging the planet towards slightly milder summers in the far north, which favours the slow growth of ice. The natural metronome is ticking toward winter. Yet when we look at measurements from thermometers, satellites, ocean buoys, and weather stations over the last 150 years, we do not see any sign of that slow cooling. Instead, the world has warmed, and not by a tiny amount. Global average temperature has climbed by more than 1 full degree Celsius since the late 1800s. That may sound small at first, like the difference between a cool and a warm day, but on a planetary scale, it is a huge shift in stored energy. The timing of that rise matters. It is packed tightly into a century and a half that coincides with a massive increase in greenhouse gases from burning coal, oil and gas, and from cutting down forests. Carbon dioxide in the atmosphere has risen from about 280 parts per million before the industrial era to more than 420 parts per million today. Ice cores show that in hundreds of thousands of years of natural ups and downs, levels never climbed this high. If orbital cycles were still in charge, we would expect a slow drift, not a sharp spike. Think about watching a tide come in at the beach. You know that over hours the water will creep up the sand. If someone suddenly opens a floodgate upstream and a surge of water rushes in, you still see the tide, but you also see a faster, more chaotic rise riding on top of it. That is what the modern warming trend looks like when placed on the backdrop of Milankovitch timing. A superimposed surge that does not match the slow beat. Climate models give us a way to test this idea. Researchers can feed only natural drivers into their equations, things like volcanic eruptions, solar variability, and orbital changes, and see what kind of climate those inputs produce. When they do that for the 20th century, the simulated planet drifts up and down a bit, but it does not show the strong sustained warming that the real Earth experienced. When they add human emissions of greenhouse gases and fine reflective particles called aerosols, the model world suddenly starts to track the real temperature record much more closely. This is not a perfect experiment. We cannot rerun Earth with and without humans. But it is one of several lines of evidence that point in the same direction. The natural cycles that steered ice ages into and out of being are still there. They still matter for the long-term trajectory of climate. Yet on the timescale of a human life, their influence is gentle, almost invisible compared with the rapid forcing from greenhouse gas buildup. The old gears are still turning, but a new motor has been bolted onto the machine. You might wonder whether there have ever been fast changes before.
The geological record does include events where climate shifted abruptly, over centuries rather than millennia. Often these are linked to sudden releases of greenhouse gases from massive volcanic eruptions or from feedbacks such as thawing permafrost. Even in those cases, however, The trigger is a physical injection of heat-trapping gases or a big change in how the planet reflects sunlight. The underlying rule is the same. Change the energy balance quickly enough and the system will scramble to adjust. Right now, that scramble is showing up in places that feel far removed from orbital diagrams. It is in the fact that summers in many regions are not just warmer, but longer, with spring starting earlier and autumn heat lingering. It is in the shrinking of mountain snowpack that farmers once relied on as a natural reservoir. It is in ocean heat content, which has been rising steadily as the seas soak up most of the extra energy trapped by greenhouse gases. The oceans are not infinite. They respond in their own ways, shifting currents and altering where storms gather and where they fall apart. This is where slow and fast begin to tangle. The orbital cycles set the overall background for ice ages. Human emissions are adding a rapid new tilt to the balance. In between lies another layer of variability that you feel much more directly. Multi-year to decadal swings in ocean and atmosphere that can make one decade wetter, another drier, one set of years stormier, another strangely calm. These internal rhythms do not care about political borders. They start with winds and water in one region and send ripples across the globe. Before we turn to those faster rhythms, it is worth pausing on one subtle point. When people say climate has always changed, they are right. What they often leave out is that the causes and speeds of those changes matter deeply. A farmer, a city planner, a coastal engineer lives on the scale of decades. The Milankovitch cycles move glacially. In practical terms, the slow march toward another ice age is irrelevant to a harbour that will be flooded or spared in the next 40 years. What matters is how quickly sea level rises and how storm patterns shift on that shorter horizon. You can think of the orbital cycles as setting the long-term contour of a mountain range. Human influence is like building a new road that snakes up one side much faster than erosion would have shaped it. And internal climate variability, driven by ocean and atmosphere dynamics, is like the day-to-day weather on that road. Fog one day, blazing sun the next. To predict the experience of someone walking along it, you need to know all three: where the mountains are, how steep the road is, and what the sky is doing overhead. The story of Milankovitch and the Ice Ages gives us confidence that we understand the first piece. It shows that Earth's climate is not random, that there are repeatable, predictable elements in its dance.
It also shows that the planet can respond strongly to relatively small nudges when those nudges persist for long enough and act in the right place. That should make us more cautious, not more relaxed, about introducing a massive new push through greenhouse gas emissions over a very short time. The question that now looms is how these ancient orbital rhythms and the new human forcing are interacting with the internal cycles of the system. When the background warms, do the natural swings of the oceans and atmosphere simply ride on top unchanged, or do they stretch, skew, and intensify? Does a familiar pattern that once brought manageable drought or gentle rains turn into something far more disruptive once extra heat is loaded into the water and air?
To answer that, we need to leave the realm of 100,000-year ice sheets and step into a pattern that unfolds over just a few years at a time, yet reaches into almost every country on Earth. It begins with a patch of warm water in the tropical Pacific and the trade winds that usually push it westward. When those winds falter or reverse, the ocean's surface rearranges itself. Storm tracks follow, and suddenly a quiet shift of heat along the equator becomes drought in one place, flood in another, wildfire in a third. In the tropical Pacific, under an ordinary year, the story begins with wind. Persistent trade winds blow from east to west along the equator, pushing warm surface water toward Indonesia and Australia.
That warm water piles up there, making the Western Pacific a deep heated pool of ocean, while cooler water wells up from the depths along the coast of South America in the east. Above that contrast, air rises over the warm pool, forming towering storm clouds, then flows high in the atmosphere back toward the east and sinks over the cooler side. This loop of air and water is one of the main engines of global weather. Fisher communities along the coasts of Peru and Ecuador have known for centuries that this engine does not always behave the same way. Some years, near the end of the year, the normally cool waters off their shores turn strangely warm.
The fish that thrive in cold upwelling water become scarce, anchovy catches crash, and rains that usually stay over the western Pacific wander east. They called this pattern the warm current of the Christ child because it tended to peak around December. Long before anyone spoke of global climate systems, they already felt the breath of a giant they could not see. Scientists later gave that giant a more technical name, the El Niño Southern Oscillation. El Niño is the warm phase of this pattern. La Niña is the cool counterpart. Southern oscillation refers to the seesaw in air pressure between the western and eastern Pacific that accompanies these swings. Together, they form one of the most important climate rhythms on the planet, with a cycle that is irregular but often falls in the range of 2 to 7 years. In a normal year, strong trade winds drive warm surface water westward and keep the eastern Pacific relatively cool through upwelling of deep water. During El Niño, those trade winds weaken, or, in extreme cases, even reverse for a time. Without the steady push, the warm water that had piled up in the west begins to slosh back toward the central and eastern Pacific. The layer of warm water spreads out, deepening the surface layer and suppressing the usual upwelling of cold, nutrient-rich water. At the same time, the focus of thunderstorm activity shifts. With warm water now covering more of the central and eastern Pacific, rising air and heavy rains follow that warmth eastward. This rearrangement of where heat and moisture move into the atmosphere sends ripples through the entire global circulation. Jet streams kink and bend into new shapes. Storm tracks shift. Regions that usually receive steady rains can dry out. Regions that are often dry can suddenly find themselves under repeated downpours. You can think of El Niño as a hand that reaches into the planetary weather machine and nudges levers in many places at once. In the western Pacific and parts of Australia and Indonesia, El Niño years often bring drought and high fire risk. In parts of the western coast of South America, they bring intense rains and flooding. Over the southern United States, winters can be cooler and wetter. In other regions, El Niño may reduce hurricane activity or shift where storms tend to form and travel. The exact pattern varies with each event, but the influence is global. Real-world examples show how powerful this pattern can be. During some strong El Niño events, Indonesia and parts of Southeast Asia have experienced severe drought, leading to widespread forest fires and haze that can blanket cities in smoke. At the same time, coastal Peru has faced torrential rains that destroy infrastructure and trigger landslides. Farmers in Africa and South America can see crops fail or flourish, depending on how rainfall patterns tilt during these years. A shift in water temperature thousands of kilometers away can decide whether fields feed families or lie cracked and barren. La Niña, the cool counterpart, pushes the system the other way. In La Niña years, the trade winds tend to strengthen rather than weaken. They push even more warm water toward the western Pacific, drawing up extra cold water in the east. The contrast between the warm west and cool east becomes sharper. Thunderstorm activity and heavy rains cluster even more toward Indonesia and northern Australia. Some regions that suffered drought during El Niño find themselves drenched during La Niña, while others flip from flood to dryness. These alternating phases mean that for many parts of the world, year-to-year swings in rainfall and temperature are not random at all. They are strongly tied to whether the tropical Pacific is in a warm, neutral, or cool state. Water managers, farmers, public health planners, and emergency responders all pay close attention to forecasts of El Niño and La Niña, because the pattern can tilt the odds of drought, flood, heat, or disease outbreaks in predictable ways. It does not decide every storm, but it loads the dice. From a scientific perspective, the challenge has been to see and understand this pattern clearly. For centuries, people only knew the local effects. Fishermen noticed warm currents and bad catches. Farmers noticed fickle rains.
With the rise of global weather stations, ocean buoys, satellites, and ship measurements, researchers could finally map sea surface temperatures and air pressure across the entire Pacific at once. That is when the full shape of the El Niño Southern Oscillation emerged. They saw that during El Niño, a band of warmer than average water stretches across the central and eastern equatorial Pacific like a glowing scar. During La Niña, a strip of cooler than average water marks the same region, while the warm pool in the west bulges stronger. These anomalies may be only a few degrees warmer or cooler than the long-term average, but because they cover such a vast area, they represent a huge amount of extra or missing heat. The atmosphere responds directly to that shift. If you like mental experiments, you can imagine the tropical Pacific as a gigantic bathtub. In neutral years, steady winds blow surface water to one end, piling it up and drawing cooler water up at the other end. In El Niño years, the winds slacken and the stacked water sloshes back toward the centre. In La Niña years, the winds blow harder and the stack grows taller. Now imagine that every slosh changes where steam rises from the tub, and that steam feeds a complex system of spinning air currents overhead. Tiny changes at the surface can reshape global patterns. One reason this matters so much is that many societies cling tightly to the edge of what their local climate can support. A few failed rainy seasons can push vulnerable communities into famine.
A few years of repeated heavy storms can erode coastlines, overwhelm drains and spread disease. Knowing that an El Niño is developing months in advance gives some warning to prepare. It does not eliminate the risk, but it can turn pure surprise into planned response. There is another layer of tension in this story. As the planet warms due to greenhouse gas buildup, scientists are trying to understand how the El Niño southern oscillation itself may be changing. Is it becoming more frequent, more intense, or skewed toward one phase? Are we entering an era where so-called super El Niño events become more likely, with even larger shifts in rainfall and temperature? This is an active area of research, and answers are not yet fully settled, but hints are emerging. One clue lies in the fact that a warmer background ocean gives every El Niño more heat to work with. When an El Niño event spreads warm water across the central and eastern Pacific, in a world that is already warmed, the resulting changes in atmospheric circulation can be stronger. Heat waves, droughts and downpours no longer play out over the climate of the early 20th century. They unfold on top of a new baseline, with more moisture in the air and less snow and ice in many regions. Another clue is that some recent El Niño events have shown unusual shapes. Rather than warmth focused mainly in the far eastern Pacific, some have featured peak anomalies more in the central Pacific.
This so-called Central Pacific or Modoki flavour of El Niño can shift teleconnections in slightly different ways, moving the regions of strongest drought or flood. If those flavours become more common, the historical patterns that communities rely on may become less reliable guides. At the same time, climate models suggest that La Niña events might also change their character in a warming world. Stronger trade winds and enhanced cooling in the east during La Niña could temporarily counteract some of the global warming signal, leading to short periods where global temperature rise seems to pause. Skeptics sometimes point to those plateaus as proof that warming has stopped, only to see global temperatures leap upward again when the pattern swings back toward neutral or El Niño conditions.
From your perspective as someone living through this, what matters is not the labels but the lived experience. A series of years dominated by El Niño-like conditions might bring repeated drought to one region and repeated flood to another. Infrastructure built for the climate of the past may fail more often. Insurance systems may strain. Migration patterns can shift as people move away from places where crops no longer grow consistently or where dangerous floods hit again and again. There is also a quieter biological story. Many marine species are tuned to the usual pattern of cold, nutrient-rich upwelling in the eastern Pacific. During El Niño, when that upwelling falters, entire food webs can suffer.
Coral reefs in warmer regions may bleach and sometimes die as water warms beyond their tolerance. Seabirds and marine mammals that depend on certain fish may face starvation. These ecological shocks ripple into human communities that depend on fisheries for food and income. One of the subtle, soft calls to action that this pattern offers is simply the need to pay attention to more than just the weather outside your window. When you see news of drought in one country and flooding in another, you can ask whether a common thread ties them together. You can look for whether an El Niño or La Niña is underway, and how that might be shaping the odds of extreme events where you live. This awareness does not change the physics, but it changes how prepared we are. Researchers are also learning that the El Niño Southern Oscillation does not operate in isolation. It can interact with other ocean cycles, such as those in the Indian Ocean or the North Atlantic, in ways that either amplify or dampen its effects. In some years, these patterns reinforce each other and produce very strong global imprints. In other years, they partially cancel out, leading to more muted consequences. Understanding these interactions is one of the frontiers of climate science. Seen from above, the whole system resembles a set of coupled oscillators, like pendulums linked by springs. Tug one, and it influences the others. Warmer region of the equatorial Pacific and jet streams thousands of kilometers away can shift their paths. Those jet streams are high-altitude bands of fast wind that guide storms across continents. In a sense, El Niño presses on the start of a chain that ends with rain or snow on your street. This connection between ocean patterns and atmospheric rivers of wind is crucial. When the tropical Pacific pumps more or less heat into the atmosphere, it changes the balance of highs and lows that shape the jet streams. Waves in those jets can become more pronounced, looping farther north and south. Some regions end up under a stagnant ridge of high pressure that brings heat and drought. Others find themselves in the persistent path of storm after storm. As the background climate warms, there is growing interest in whether these jets and their waves are also changing.
Are they becoming more meandering, more prone to getting stuck in certain configurations? Such stuck patterns can bring long-lasting heat waves or prolonged wet spells. The El Niño Southern Oscillation might act as a trigger that nudges the jets into one of several possible shapes, while the warmed atmosphere decides how intense the resulting extremes will be. To fully grasp this, we now need to shift our view from the surface of the Pacific up into the sky. There, at the boundary between different air masses, high-speed winds circle the planet like invisible rivers. They are shaped by the contrast between equator and pole, and by the spin of Earth itself. When those rivers flow smoothly, weather can be fairly predictable. When they buckle and twist, the consequences can be dramatic.
To see how that happens, we have to step into the world of jet streams and the polar vortex, the walls of wind that hold the cold in place until they suddenly do not. High above the surface, the air does not just drift aimlessly. It organizes itself into vast belts and rivers, shaped by sunlight, rotation, and the curve of the planet. Warm air near the equator rises, flows toward the poles, cools and sinks, creating giant circulation cells stacked from equator to mid-latitudes and from there toward the poles. As the air moves, Earth spins beneath it, twisting straight paths into curves. Out of this slow ballet emerge narrow bands of very fast winds that wrap around the globe. These are the jet streams, and they are the tracks along which much of our weather rides.
There are two main families of jets in each hemisphere. One set, called subtropical jet streams, forms near the edges of the tropical circulation, where rising warm air from near the equator meets cooler air from higher latitudes. Another set, called polar front jets, forms where cold polar air battles with warmer air from the mid-latitudes. The stronger the temperature contrast between these air masses, the stronger the jet. In winter, when the difference between frigid polar night and sunlit lower latitudes is greatest, these wind rivers can roar at hundreds of kilometers per hour. To a pilot, they are both a blessing and a danger, helpful tailwinds in one direction and fierce headwinds in the other. If you could see a jet stream from space, it would look like a sinuous band of fast air snaking around the hemisphere. It rarely forms a perfect circle. Instead, it meanders north and south, forming large waves. Where the jet arches northward, warm air intrudes toward the pole. Where it dives southward, cold air plunges toward the equator. Those loops steer storm systems, decide where rainstorms linger, and where high-pressure domes can trap heat or cold in place for days or weeks. Deeper over the poles, above the level where jets patrol the boundary between air masses, lies another structure. In winter, when the polar regions are plunged into long darkness, the air high in the stratosphere cools dramatically. This cold air, surrounded by warmer air farther south, begins to spin under the influence of Earth's rotation. The result is a swirling pool of frigid air that circles the pole at high altitude. This is the polar vortex, not a single storm, but a persistent whirl of cold held in place by strong westerly winds. You can imagine the polar vortex as a vast cold reservoir with a spinning wall of wind around it. As long as that wall stays strong and fairly circular, most of the bitterest air stays penned up near the pole. The mid-latitudes may get chilly, but the deepest cold remains locked away. When the vortex is tight and stable, winters in many populated regions can be relatively mild and consistent. It is only when that circulation weakens, stretches or splits that things get interesting and often dangerous for people living far from the Arctic. Sometimes, waves in the jet streams below grow large enough to send pulses of energy upward into the stratosphere. When that energy breaks there, like ocean waves crashing on a shore, it can rapidly warm the stratospheric air above the pole. This event is called sudden stratospheric warming. Temperatures high over the polar region can rise by tens of degrees in a matter of days, even while the surface remains bitterly cold below. The warming disrupts the polar vortex, weakening its winds and often displacing or splitting the cold pool.
When the vortex is disturbed in this way, the cold air that was swirling neatly over the pole can leak out in long tongues. One lobe might spill south over North America, another might plunge into Europe or Asia. At the surface, people simply feel this as a brutal cold wave. Temperatures fall far below seasonal norms, rivers ice over quickly, snowstorms can tap into the frigid air and become more intense. Energy grids strain under high heating demand. People may hear the phrase polar vortex in the news and imagine something new, but the core physics have been part of the atmosphere's behaviour for a long time. In recent decades, several dramatic cold outbreaks have been linked to disrupted polar vortices. Cities that usually only flirt with freezing temperatures have seen fountains turn to ice and pipes burst. Regions that pride themselves on dealing with winter have still struggled when repeated waves of Arctic air kept arriving. These events are powerful reminders that a warming planet does not mean an end to severe cold. Instead, it can mean more volatility, with sharp swings between unseasonal warmth and intense cold. The question many researchers are grappling with is whether climate change is making these disruptions more likely or more severe. One idea suggests that as the Arctic warms faster than the rest of the planet, the temperature contrast between pole and mid-latitudes decreases. Since that contrast helps drive the jet streams and maintain the polar vortex, a reduced difference could weaken those winds. Weaker winds are more prone to wobbling, buckling, and allowing cold air to escape southward. In this view, a gentler gradient can mean a messier, more contorted set of jets. Evidence for this is still being debated. Some studies find that winters with a weakened polar vortex and more extreme mid-latitude cold have become more common in certain regions. Others point out that natural variability is large and records are short. What is clear is that when the vortex does break down, the impacts now unfold against a warmed background climate.
That means that while cold extremes still happen, warm extremes are climbing faster, and snow and ice cover can melt more quickly when a warm spell follows a cold outbreak. From your perspective on the ground, you do not feel jet streams or polar vortices directly. You feel their influence as a pattern of days that suddenly tilt one way or another. A winter that starts gently may snap into a deep freeze after a stratospheric event. A sequence of storms may trace along the same path because the jet stream has settled into a stuck shape, looping repeatedly over the same region. The atmosphere loves to find certain favoured patterns and linger there for a while. When those patterns are amplified, the lingering can become dangerous.
Think about the heat domes that have baked parts of North America and Europe in recent years. In many cases, a sprawling ridge of high pressure became locked in place by a warped jet stream. Under that ridge, sinking air suppressed clouds and trapped heat. Nights offered little relief. Wildfires flared in dry forests, crops wilted. At the same time, on the other side of that warped jet, cool and rainy conditions persisted. The same wavy pattern that delivered kindness to one region delivered stress to another. The interplay between jet streams, polar vortices, and lower-level weather systems is complex, but one theme keeps returning. Small shifts in the large-scale flow of air can lead to big differences in local experience.
If a jet loop sits a few hundred kilometers farther north or south, the boundary between mild and frigid conditions moves with it. Where that boundary lines up with coastlines, mountain ranges, or urban corridors can decide whether a winter is remembered as harsh or uneventful. Forecasting these shifts has improved dramatically with satellite data, high-resolution models, and better understanding of the underlying physics. Meteorologists can sometimes see a sudden stratospheric warming event brewing weeks in advance and warn that the polar vortex is about to wobble. That gives energy providers, city planners, and emergency services time to prepare for the possibility of severe cold. Yet the details remain hard to pin down. Knowing that the vortex is weakening does not always tell you exactly which region will get hit hardest. As the climate system warms, this uncertainty gains extra weight. A storm that once would have brought a certain amount of snow may now bring more rain instead, or a dangerous mix of ice and heavy wet snow that threatens power lines. A cold outbreak may hit a landscape where plants and animals have already been nudged into early spring by prior warmth, making them more vulnerable. The same physical event ripples through a world whose baseline has shifted, often in subtle ways that only become obvious afterward. You can think of the polar vortex and the jet streams as guardrails for seasonal weather. When they behave, cold stays mostly where you expect it. Storms follow familiar corridors, and extremes are less frequent. When those guardrails bend or break, air masses wander freely, and the deck of possible weather outcomes is reshuffled. Climate change does not remove the guardrails, but it may be loosening some of the bolts that hold them in place. There is another aspect of wind that is easy to overlook. High in the atmosphere, especially in the stratosphere, air motion is influenced not only by temperature gradients and rotation, but also by the flow of energy from above. Solar storms that send charged particles hurtling toward Earth can deposit energy in the upper atmosphere, altering its structure. Changes in ultraviolet output from the sun over its activity cycle can also subtly warm or cool different layers. These effects are small compared with greenhouse gas forcing, but they remind us that our atmosphere does not sit in isolation. It is constantly negotiating with space. When particles from the sun arrive, most of them do not slam directly into the lower atmosphere. They are guided and deflected by Earth's magnetic field, which shapes regions where charged particles spiral and collide with air molecules. Those collisions create auroras near the poles, shimmering curtains of light that reveal invisible currents overhead. At the same time, they can perturb the circulation of the upper atmosphere and generate waves that propagate downward, sometimes nudging the polar vortex or influencing jet behavior in ways scientists are still trying to fully understand. All of this rests on the presence of a magnetic shield that extends far beyond the clouds. Without that shield, our atmosphere would be more exposed to harsh solar and cosmic radiation. Satellites would suffer more frequent damage. The upper layers of air could be stripped away more quickly over geological time. The same flows in Earth's molten core that generate this magnetic field also drift and wobble, and over long spans, they even flip. The north and south magnetic poles have traded places many times in the deep past. When you watch videos of auroras flickering over snowy forests or frozen seas, you are really seeing energy from the sun tracing the lines of that magnetic field. You are also seeing a hint of the vulnerability of our technological world. A strong geomagnetic storm can induce currents in power lines, disrupt communication systems, and strain satellites. These events are most likely when the sun is near the peak of its activity cycle, and when the geometry between solar eruptions and Earth's field lines lines up just wrong. The jet streams and the polar vortex show us how the atmosphere responds when energy moves around within the system. The auroras and geomagnetic storms show us what happens when energy arrives from outside and the magnetic field catches it.
We have learned a great deal about these processes, but there is still a deeper question lurking. How stable is that magnetic shield itself, and what happens to Earth's surface and its life when the field weakens or reconfigures during one of its occasional flips? Deep under your feet, far below the crust and the mantle, there is a kind of weather that never reaches the sky. It is not wind and rain. It is liquid metal in motion, swirling, rising and sinking in darkness. That hidden storm is what keeps your compass honest, your atmosphere shielded, and most of the worst radiation at bay. When we talk about Earth's magnetic field, we're really talking about that restless outer core and the electric currents it constantly generates. As long as those currents flow in a roughly organised way, we get the familiar pattern of a magnetic north and south and a shield that stretches far into space. Earth's interior is layered. At the centre sits a solid inner core of mostly iron and nickel under crushing pressure. Around it is a shell of molten metal, the outer core still iron-rich but hot enough to flow like an incredibly dense, slow liquid. Above that sits the rocky mantle and finally the thin crust that carries continents and oceans. The outer core is where the magic happens. When metal moves through an existing magnetic field, it generates electric currents, which in turn create more magnetic field. This feedback loop, called a dynamo, is what powers Earth's magnetism. The flow in the outer core is driven by heat escaping from deeper within the planet, and by lighter elements rising while heavier ones sink. You can picture great looping currents of molten iron, rising as they warm, spreading, cooling, and sinking again. Because Earth is spinning, these flows do not rise and fall in straight lines. They twist into spirals, much like water in a rotating bucket. The result is a tangled, three-dimensional pattern of motion that nevertheless, on average, produces a relatively simple dipole field with a general north and south. That field extends far beyond the surface, shaping a bubble in space called the magnetosphere. Charged particles streaming from the sun, carried by the solar wind, slam into this bubble. Many are deflected around it, like rain flowing around an umbrella. Some are trapped in belts of radiation that circle the planet. Others spiral down near the poles, colliding with atoms in the upper atmosphere and making them glow. That glow is the aurora, the northern and southern lights, a visible reminder that something invisible is working to protect us. Without this magnetic shield, life on the surface would not suddenly die. Earth's thick atmosphere also blocks and scatters damaging particles and ultraviolet light. But over long times, a missing magnetic field could allow the solar wind to strip away more of that atmosphere, especially the lightest gases. Mars is a sobering example. Once it may have had a stronger magnetic field and thicker air. As its interior cooled and its dynamo faded, its shield weakened, and the solar wind had a clearer shot at slowly eroding its atmosphere. Earth's field is not as steady as a bar magnet on a desk. It drifts, wobbles, and changes strength. Compasses that once pointed to a magnetic north somewhere in northern Canada have had to adjust as that pole has raced towards Siberia. Measurements show that the field strength at the surface has varied over time. Today, on average, it is still robust, but there are regions where it is noticeably weaker. One of those regions has become a particular focus of concern, because it sits over an area where many satellites pass. This region is known as the South Atlantic Anomaly. It lies roughly over parts of South America and the South Atlantic Ocean.
In this area, the inner radiation belt dips closer to Earth than usual because the magnetic field there is weaker and oddly shaped. Satellites that pass through the anomaly are exposed to higher fluxes of energetic particles. Sensitive electronics can experience glitches. Instruments may be switched off temporarily to avoid damage. Even the Hubble Space Telescope has to suspend some operations when it flies through this zone. The anomaly is not a hole in the shield. The field is still there, still deflecting most particles, but it is a hint that the magnetic field is not a rigid, unchanging structure. It is more like the weather in the core, shifting and evolving. That raises a larger question.
If parts of the field can weaken and distort, could the entire global pattern change, even flip? The answer, written in rock, is that it has many times. When lava erupts and cools, tiny grains of iron bearing minerals inside it can align with the local magnetic field, like millions of microscopic compass needles freezing in place. Over vast stretches of time, new lava layers pile up, sometimes on the ocean floor, sometimes on land. By sampling and dating these rocks, scientists have discovered a striking pattern. The direction of the recorded magnetization flips back and forth. For long periods, magnetic north is near the geographic North Pole. Then, after a transition, magnetic north sits near the geographic South Pole.
These reversals have happened hundreds of times over the last many millions of years. On average, full reversals seem to occur every few 100,000 years, but the timing is irregular. Some intervals between flips are longer, some shorter. The last full reversal, known from marine sediments and lava flows, occurred about 750,000 years ago. That means we have been in the same general configuration for longer than usual. This has led some people to wonder whether we are overdue for a flip. The South Atlantic Anomaly and the rapid motion of the magnetic poles have added fuel to that speculation. During a reversal, the field does not simply vanish overnight, then reappear pointing the other way. It is a gradual, messy process that may take thousands of years. As the outer core flow reorganizes, the field can weaken, its main dipole component shrinking, while smaller scale, more complex patches grow. At the surface, this would mean that the field might be reduced to a fraction of its current strength for a time, with multiple north and south-like regions scattered around the globe instead of a tidy two-pole structure. Some estimates suggest that, during the weakest phases of past reversals, the overall field may have dropped to around a tenth of its usual strength. That is not certain, but it gives us a rough sense of the scale. A weaker field would allow more charged particles from the Sun and cosmic rays from deep space to reach lower altitudes. Auroras might be visible much farther from the poles.
Satellites in low and medium orbits would be exposed to higher radiation doses. Astronauts passing through vulnerable regions would face more risk. High-altitude flights on some routes could see increased radiation exposure. It is not hard to imagine dramatic headlines. Planet losing its shield. Reversal will fry electronics. Life at risk. Some studies have even suggested that a particularly weak interval in the field's recent history might have coincided with climate shifts and stress on certain species, perhaps contributing to extinctions in some regions. One analysis of a field-weakening event roughly 40,000 years ago proposed links to changes in atmospheric chemistry and environmental upheaval that would have challenged early humans and other creatures.
At the same time, we have to put those fears next to a broader record. Geologists can trace many past reversals in rock without seeing corresponding global mass extinctions. Life did not collapse every time the field flipped. Dinosaurs, early mammals, and countless other organisms lived through many reversals without obvious catastrophe. That does not mean there were no regional impacts or stresses. It does mean that the planet's basic habitability persisted. The atmosphere is a powerful shield in its own right, and even a weakened magnetic field still offers protection. From the perspective of modern civilization, the main risks would likely be technological. Satellites might fail more often, or need more shielding and careful routing. Power grids could be more vulnerable to geomagnetically induced currents during strong solar storms, especially at higher latitudes, where magnetic field lines connect more directly to space. Communication and navigation systems that rely on the field, or on satellites, could face more disruptions. Radiation doses on certain flight paths might rise, requiring changes to routes or altitude. The good news is that reversals unfold slowly on human timescales. If we saw clear signs that a major transition was underway, we would have centuries to adapt. Spacecraft design could evolve to handle a harsher radiation environment. Power systems could be hardened. Monitoring networks could be expanded and improved. Unlike a sudden asteroid impact, a field reversal is not a bolt from the blue. It is a process that creeps. The more closely we watch the field, the more warning we will have. This does not mean we can shrug off current anomalies. The South Atlantic Anomaly already forces engineers to plan around it. As it drifts and perhaps expands, more satellites will have to deal with its effects. Magnetic navigation in some regions can become slightly less reliable if the field changes rapidly. Animals that sense the field, like migratory birds, turtles, and some fish, may need to adjust their internal maps. There is evidence that many species already cope with natural field variations, but rapid shifts could still pose challenges.
One subtle, soft lesson in all of this is that our dependence on technology has tied us more tightly to the state of the magnetic field than any previous civilization. Ancient humans could have lived through a reversal with little direct awareness beyond beautiful lights in the sky and perhaps some changes in climate or ecosystems. We live inside a shell of electronics. Positioning, timing, power distribution, communication, and observation all flow through satellites and long conductors that can be nudged by space weather. Knowing that, you can start to see the magnetic field not as an abstract geophysical curiosity, but as part of the infrastructure that supports your daily life.
When your phone finds your location, when a ship navigates a crowded harbour, when a plane follows a route across the ocean, there is usually some combination of magnetic and satellite-based guidance at work. When a strong solar storm disturbs the field, those systems can glitch. If that disturbance is layered on top of a weakened or oddly shaped field, the effects can be more complex. This connection to solar storms is what makes the magnetic field's strength and configuration more than an academic issue. The sun is not a steady light bulb. It has its own cycles of activity, with peaks where sunspots, flares and eruptions are more common. When a coronal mass ejection, a huge bubble of magnetized plasma, is launched toward Earth, it carries its own magnetic field. If that field happens to connect efficiently with Earth's, energy can pour into the magnetosphere, bending and shaking it. Currents are induced in the ground and in power lines. Radiation belts swell. In a strong storm, satellites can be damaged or knocked offline. Radio communication can be disrupted over large regions. Power transformers can overheat. In rare cases, grids have suffered blackouts when geomagnetic storms induced currents beyond what they were built to handle. So far, we have mostly been lucky. The strongest storm in recorded history, in the 19th century, happened before the modern electrical age. If a storm of similar magnitude hit today, it would be a much more serious test. A weaker magnetic field during a reversal would not increase the number of such solar eruptions, but it could change how their energy couples into our environment. More particles could reach orbits that are usually safer. The region of atmosphere where they interact could shift. How severe that would be in practice is still under study. We do not have a direct modern example of a full reversal to examine, only partial field changes and models built on physics. All of this might sound like an extra layer of worry on top of everything else, yet there is another way to look at it. Earth has lived with a restless core and a temperamental sun for billions of years. Life has persisted and diversified through many flips, excursions, and storms. What is new is our awareness and our ability to prepare. Space weather forecasting is improving. Field measurements from satellites and ground stations are building a detailed record of how the magnetosphere responds to solar moods. If you want a mental image to carry forward, picture the planet as a set of nested shields. At the centre, movement in the core generates a magnetic field that shapes a protective bubble. Above the surface, the thick blanket of air blocks and scatters dangerous particles and light. At the very top, technology watches the sun, tracks eruptions, and warns us when big storms are on the way. Each layer has its own vulnerabilities. Together, they make Earth far less fragile than the phrase, "losing our shield," might suggest. Still, the idea that the ground beneath you is slowly churning and flipping the sky's invisible compass is a reminder that even what feels permanent is in motion. The magnetic poles will continue to drift. The South Atlantic Anomaly may grow, shrink, or split. At some point in the future, the field will likely reverse again. What matters for us is not whether that happens in 10,000 or 1 million years, but how we handle the much sooner tests. Those tests are already arriving in the form of solar storms and the 11-year rise and fall of solar activity. Every cycle brings new flares, new auroras, and new chances for our technology to be pushed and stressed. To understand how that heartbeat of the sun works, and how it ties into everything from power grids to the faint statistics of climate variability, we have to lift our gaze from the core to the star that feeds energy into every other cycle we have met so far. If you have ever seen a picture of the sun from a space telescope, you know it is not a calm golden disk. It is mottled with dark patches and bright loops, riddled with arches of plasma and flickers of light. On human timescales, it rises and sets with comforting regularity. On its own timescale, it pulses and changes. One of the most important patterns in that change is a roughly 11-year rhythm. Over that cycle, the number of visible sunspots rises from almost none to many, and then falls again.
Along with those spots come bursts of energy that can rattle not only Earth's magnetic field, but also the technology we use every day. Sunspots themselves are relatively cool regions on the solar surface, dark only by contrast with their surroundings. They mark places where intense magnetic fields poke through the surface, twisting and tangling. Those magnetic tangles store energy. When they snap and reorganize, they can release that energy in explosive events called solar flares. Flares flood space with bursts of radiation across the spectrum, including X-rays and energetic particles. Sometimes, the same tangled regions also launch huge bubbles of charged gas into space. These are coronal mass ejections, immense clouds of plasma threaded with magnetic fields.
At times of solar maximum, when the sun is most active in its cycle, sunspots are numerous. Flares and eruptions are much more likely. The solar wind, a constant outflow of charged particles, becomes gustier. At solar minimum, by contrast, the sun's face can be nearly spotless for weeks, and large eruptions are rarer. This waxing and waning does not change the total brightness of the sun very much. The energy reaching Earth's surface varies only slightly, a change too small to drive the kind of rapid warming we are seeing today. Yet the changes in particle flux and magnetic environment are large enough to matter for space weather and for some subtle climate patterns. When a coronal mass ejection is launched in just the wrong direction, it can intersect Earth's orbit.
If that happens and the orientation of its magnetic field lines is favourable for connection, a huge amount of energy can pour into the magnetosphere. Field lines stretch and snap, currents surge, and the auroras brighten and expand toward lower latitudes. What might normally be confined to polar skies can spill into regions that rarely see such displays. People who have never looked up to find curtains of green and red swaying overhead suddenly feel like they are living inside a planet-sized laboratory. These events are beautiful, but they come with costs. The same currents that paint the sky can induce electrical flows in long conductors on the ground. High voltage power lines, which span hundreds of kilometers, are particularly susceptible. Extra current can overload transformers and damage them. In the past, strong geomagnetic storms have caused widespread outages in parts of Canada and northern Europe. In an extreme case, a storm could knock out power for large areas for hours or days, and damage some equipment that takes months to replace. Satellites are on the front line. When a solar storm hits, the charged particles can penetrate satellite materials and build up charge in the electronics. That charge can suddenly discharge, causing glitches or permanent failure. Radiation levels in certain orbits can spike. Communication and navigation signals that pass through the disturbed layers of the atmosphere can be degraded or temporarily lost.
Space agencies track solar activity closely because a single, poorly timed storm can threaten fleets of spacecraft. Even without major storms, the steady beat of the solar cycle nudges Earth's upper atmosphere. During solar maximum, increased ultraviolet radiation from the sun heats and puffs up the thin air high above the surface. This expansion increases the drag on satellites in low Earth orbit, causing them to lose altitude more quickly if their paths are not adjusted. Old debris also decays faster, which can be a mixed blessing, reducing clutter over time but complicating predictions in the short term. You might wonder whether this cycle leaves any imprint on climate nearer the ground. The answer is that it does, but in subtle ways. The direct change in the sun's total energy output over the cycle is small compared with the forcing from greenhouse gas increases. However, changes in ultraviolet light and in the flux of charged particles can influence the chemistry and temperature of the upper atmosphere. This in turn can modestly alter the patterns of winds that descend through the layers below. Some studies have found faint echoes of the solar cycle in regional climate statistics. For example, certain patterns of winter circulation over the North Atlantic and Europe appear slightly more likely during specific phases of solar activity. There are hints that rainfall in some monsoon systems responds weakly to the solar rhythm.
A few analyses have even suggested small correlations with phenomena like lightning frequency or storm tracks. These effects are not strong enough to dominate year-to-year weather. They are buried under the much larger influence of internal variability and human-driven warming. Yet they are real enough to remind us that even the distant heartbeat of the sun is part of Earth's story. The temptation is always there to reach for dramatic claims. It can be attractive to say that solar cycles explain all modern climate change, or that they control human moods and histories in some direct way. When researchers test those claims against data, they fall short. The timing of modern global warming does not match the modest variations in solar output. Human emissions of greenhouse gases provide a much better fit to the observed pattern and magnitude of change. The solar cycle is a background pattern, not the main driver, in the recent climate record. However, when strong solar storms do hit, their immediate effects on human systems can be more than background noise. Consider aviation. High-altitude polar routes, popular for long flights between North America and Asia or Europe and Asia, pass through regions where radiation levels are already higher. During intense solar particle events, airlines may reroute flights to lower altitudes or different paths to reduce crew and passenger exposure and to avoid communication disruptions. These choices cost time and fuel, but they are part of adapting to a star that occasionally throws tantrums.
Astronauts aboard space stations or on future missions to the Moon and Mars face even greater stakes. A large solar energetic particle event can deliver doses that might be dangerous without adequate shielding. Mission planners keep a close eye on solar forecasts and design habitats with storm shelters where crews can retreat if necessary. In that sense, the solar cycle becomes not just a scientific curiosity, but a practical scheduling concern. Launch windows, spacewalks, and deep space operations all have to factor in the sun's moods. If you enjoy patterns, think about how different cycles we have met stack together. The slow dance of Earth's orbit sets the rhythm of ice ages. The multi-year swings of the tropical Pacific tilt the odds of drought or deluge. The shifting strength of the polar vortex can open or close the gate of Arctic cold. On top of these, the 11-year cycle of solar activity modulates the background of space weather and nudges the upper atmosphere. None of these cycles acts alone. Their combined effects create a shifting mosaic of risk and opportunity. One way to feel this more concretely is to imagine a period when several cycles line up. Picture a warm phase of the tropical Pacific that brings drought to one region and flood to another. At the same time, a weakened polar vortex sends waves of cold southward in winter. Then a solar maximum arrives, bringing a higher likelihood of geomagnetic storms. In such a period, a region might see strained crops, stressed infrastructure, and vulnerable power grids all at once. If a major solar storm hits while those systems are already fragile, the shock can be amplified. Now imagine the same cycles in a different arrangement: a quiet sun, a neutral Pacific, a strong and stable polar vortex. The same region might enjoy relatively gentle weather and fewer technological disruptions. Even if greenhouse gas levels are the same in both scenarios, the lived experience is very different. That is why understanding and monitoring these cycles is not just scientific bookkeeping, it is part of managing risk in a complex world. Looking ahead, there is ongoing work to improve forecasts of solar activity. We can already predict the broad phases of the cycle, knowing roughly when the next maximum is due. Predicting individual flares or eruptions is much harder. It requires understanding the magnetic field on the sun in great detail and modelling how it evolves. Instruments that map the solar surface and atmosphere in multiple wavelengths, along with spacecraft that sit upstream of Earth and sample the solar wind, are slowly improving our ability to see trouble coming. On Earth, we can harden systems against known types of disturbances. Power companies can install equipment that resists or sheds geomagnetically induced currents. Satellite builders can add shielding and design electronics with redundancy. Operators can plan to switch off vulnerable instruments during known storms. Even simple measures, like having transformers in reserve and clear protocols for responding to alerts, can make a big difference. In all of this, awareness is as important as hardware. Knowing that a storm is coming turns a random hit into a managed event. There is a quieter, almost poetic side to the solar cycle as well. Ancient peoples watched the sun with awe and sometimes fear, but they did not know that its surface seethed with magnetic storms. Today, you can follow that activity in near real time, seeing images of sunspots and flares posted hours after they occur. You can watch as the sun rises toward a maximum in activity and then relaxes again. You can even, if you live at the right latitude or travel there, plan trips to see auroras during active periods. When you stand under an aurora, it is easy to feel like a spectator in a cosmic show. Curtains of light ripple and twist, with colours that seem unreal, yet you are also standing at the end point of a chain of events. Magnetic fields tangled on the sun, plasma launched into space, that plasma interacting with Earth's magnetosphere and atmosphere, electrons colliding with atoms high above you. The same physics that threatens a satellite is what paints the sky. It is a reminder that beauty and risk often share an origin. With all this talk of cycles, storms and shields, it is easy to forget another celestial partner that plays a quieter but very direct role in your daily life. You feel its influence in the rise and fall of ocean tides, which shape coastlines and harbour traffic. You see it in the timing of some animal behaviours and in ancient calendars.
While the sun drives the major flow of energy, the moon tugs constantly at Earth's oceans, creating rhythms that repeat twice a day, twice a month and over decades. For most people, tides are simply a backdrop. Wet sand at low tide, narrow beaches at high tide. Yet hidden within those familiar swings is a slower oscillation that is about to matter a lot more than it has in living memory. The angle of the moon's orbit around Earth slowly wobbles through a cycle that takes just under 20 years. As that nodal cycle unfolds, it changes how often tides align with the sun in a way that produces especially high or low water. On a stable coast, that would already be important. On coasts where sea level is rising, it becomes a countdown. Tides begin with a simple pull.
The moon's gravity tugs more strongly on the side of Earth facing it than on the far side. The oceans bulge slightly under that uneven pull, and as Earth turns, coastlines pass through these bulges. Water rises, then falls, in a rhythm so steady that humans used it to plan fishing trips and harbour entries long before anyone knew what gravity was. Layered on top of the moon's influence is the pull of the sun. When the moon and sun line up with Earth, tides are stronger. When they are at right angles, tides are weaker. Most of us experience this as a familiar pattern. 2 high tides and 2 low tides in a day in many places, with some extra high tides around full and new moons. Calendars and tide tables capture this short rhythm. Sailors, surfers and coastal residents learn to read it almost by instinct. Yet hidden inside these predictable daily and monthly swings is a slower oscillation, one that does not show up in a casual glance at the shoreline, but becomes clear when you track tides over years and decades. The key is that the moon's orbit around Earth is not aligned exactly with Earth's equator. It is tilted. Where the plane of that orbit crosses the plane of Earth's equator, we imagine 2 invisible points called nodes. Over about 18.5 years, those nodes slowly drift, completing a full circle. This gentle wobble of the orbit changes the angle from which the moon pulls on Earth's oceans. It does not change the existence of tides, but it modulates how strong or weak they can be at particular places and times. When the nodal cycle is in one phase, the geometry makes the difference between the daily high tides and low tides slightly smaller. In another phase, it stretches that difference. High tides can climb higher above the average, and low tides can fall lower. The effect is not dramatic in a single day. You do not suddenly see a 3-metre wall of water where there was none. Instead, over years, a pattern emerges. For a run of years, the highest tides of each month reach a little higher than they did in the quiet phase of the cycle. On a stable planet, that slow breathing of the tides would simply be another part of the background. Coastal communities might notice that some decades bring more frequent, very high tides, and adjust routines around that fact. In a world where sea level is rising, though, the timing of this nodal peak matters in a new way. A coast that already sits closer to the edge of flooding because the average sea level has crept up does not need a huge extra push. A few more centimetres of high tide can be enough to tip roads, basements, and storm drains into regular trouble. You can see the beginnings of this in what has come to be called nuisance flooding. These are days when there is no storm overhead, no hurricane offshore, no extraordinary rainfall, yet streets near the shore still fill with water. Drains backflow, parking lots puddle with salty water that kills grass and corrodes cars. Locals start to learn which routes stay dry at the highest tides and which must be avoided. It is not a cinematic disaster. It is an inconvenience that returns often enough to reshape habits. Tide gauge records along many coasts show that the number of these minor flood days has been rising over recent decades. That trend has a few ingredients. Global sea levels have been climbing as the ocean warms and expands and as land ice melts. Some coastal regions are also sinking slowly as sediments compact or groundwater is pumped out. On top of that slow creep, the lunar nodal cycle can add periods where tides naturally run higher. When those threads coincide, what used to be a rare annoyance can become a frequent one.
Scientists have taken those long tide records and combined them with projections of future sea level rise and with the known schedule of the nodal cycle. Because the moon's orbital wobble is so regular, we can say with confidence when the next amplifying phase of the cycle will hit. In the middle of the 2030 decade, the nodal cycle will again lean toward making high tides higher in many locations. By that time, sea level along many coasts is expected to be noticeably higher than it is today if current trends continue. Put those pieces together and a picture emerges. In some low-lying coastal cities and towns, the number of days each year with minor high tide flooding could jump sharply.
Instead of a handful of wet days, there could be dozens, even more, depending on local conditions. Each individual flood might still be shallow, a few centimetres on a road, a trickle into a basement, but the repetition wears on infrastructure and on people. Drains fail more often, building foundations are soaked more frequently, salt water corrodes pipes and cables that were never meant to be submerged so often. Although these projections are built on numbers and models, you can feel them through everyday scenes. Imagine a small coastal neighbourhood where an elderly resident has lived for 40 years. When they first moved in, the highest tides of the year may be lapped at the edge of the street once or twice. People would come out to watch. It was a novelty.
Decades later, those same tides, riding on higher average sea level and a favourable phase of the nodal cycle, might push water well over the curb many times a month. What was once an event becomes routine. There is another layer of risk when high tides coincide with other extremes. If a heavy rainstorm arrives during a high tide, drains that normally carry water away may instead be full of seawater pushing inland. Flooding can become deeper and more widespread than it would have been under the same rain alone. If a storm surge from a tropical cyclone rides in on top of an already elevated high tide, the peak water level at the shore can be significantly higher. The lunar nodal cycle does not create the storm, but it helps set the stage for how bad the outcome can be. Coastal engineers have begun to incorporate these phases into their planning. When designing seawalls, raising roads, or upgrading drainage, they cannot only look at the tides of the last decade. They have to consider the tides they expect in the next few cycles of the moon's wobble, and how those tides will sit atop projected sea level. It is not enough to ask whether a structure can survive a certain water level today. We need to ask whether it can tolerate higher high tides 20 or 30 years from now, because the infrastructure we build now is likely to still be in place then. Some communities are exploring softer, more flexible defences in addition to hard barriers.
Restoring or preserving wetlands, marshes and mangrove forests along the coast can provide space for water to spread without immediately hitting buildings and roads. These living shorelines can absorb wave energy, slow erosion, and give high tides somewhere to go besides into human structures. They also provide habitat for wildlife and can store carbon in sediments. The challenge is that they need physical room to migrate inland as sea level rises, which means making difficult choices about which areas to protect and which to let go. The nodal cycle also offers a kind of test for our ability to use foreknowledge. Unlike many climate-related risks, this one comes with a clear timetable. We know when the next amplifying phase is coming, down to the year. We know roughly how much higher average sea level is likely to be under different emission scenarios. We can map which neighbourhoods, roads, and critical facilities sit within the reach of slightly higher high tides. The question is whether we act on this knowledge early or wait until repeated nuisance floods force more urgent responses. There is a psychological trap here. Humans adapt quickly to slow change. When a street that floods once a year begins to flood 5 times a year, residents grumble and adjust. They buy taller boots. They move their cars more often. When it becomes 10 or 15 times a year, some move away, but many cannot or do not. The transformation of that street from reliable to unreliable can pass without a single dramatic moment. The nodal cycle, by temporarily accelerating the shift, may make the change visible enough that it cannot be ignored. At the same time, not every coast will feel this cycle in the same way. The shape of the shoreline, the depth of the continental shelf, the resonance of local bays, and the distribution of land and sea all influence how lunar and solar pools translate into actual water levels. Some regions will see stronger modulation of their tides, others will see weaker effects. Local subsidence or uplift driven by geology and human activity adds another layer. This means there is no single global script. Each coastline has its own version of the nodal story. From our vantage point, though, one common theme stands out. We have reached an era where stacking cycles matters.
A tide that would have been harmless on top of the sea level of 1970 may be damaging on top of the sea level of 2035. A moderate storm surge that once stayed below critical infrastructure might cross that threshold when added to a nodal high tide and a background rise in ocean height. The word compound appears more often in discussions of risk. Compound flooding, compound heat and humidity, compound stress on systems that were designed for a calmer baseline. There is also a cultural dimension. Some communities have deep identities tied to the sea. Fishing towns, port cities, island nations. For them, retreat from the shoreline is not just an economic or engineering question. It is about heritage, language, and a sense of home.
As nodal peaks and rising seas push water farther inland, these communities face choices that cut to the core of who they are. Do they build higher walls? Do they gradually elevate buildings? Do they move entire neighbourhoods? Do they reshape their economies away from the most exposed areas? In some places, creative adaptations are already taking shape. Houses on stilts are being elevated further. Floating structures are being tested. Roads are being designed to tolerate occasional flooding rather than to exclude it at all costs, with materials and layouts that allow quicker drainage and less damage. Early warning systems for high tides and compound flood events are being refined.
These efforts are uneven, often constrained by resources and politics, but they show that living with cycles does not have to mean suffering blindly under them. The lunar nodal cycle is a reminder that not all the changes we face are surprises. Some are written into the mechanics of the Earth-Moon system and can be forecast decades in advance. Sea level rise, driven largely by our emissions, is also not a mystery. It is the predictable consequence of known physics. When you add those two together, you get a rare opportunity. We can point to a specific upcoming window of heightened risk and say, this is coming, and we still have time to decide how prepared we will be when it arrives. There is a subtle invitation here to think differently about responsibility. It would be easy to blame the moon when streets flood more often in the mid-2030s. After all, the nodal cycle is natural. It has been running since long before humans walked upright. But the reason those higher high tides will reach farther is that the baseline sea level has been lifted by human activity. The moon provides the rhythm. We have turned up the volume. Both truths can be held at once. As we trace these cycles, from deep orbital mechanics to ocean oscillations, polar winds, magnetic flips, solar pulses, and lunar nodal swings, a pattern emerges. Again and again, we find that Earth systems have their own clocks, their own ways of moving energy and matter around. For most of history, those clocks ticked without our awareness. Now we can read them.
The unsettling discovery is that our species has become large enough and active enough to be counted among the forces that shape the long-term state of the planet. That realization brings us to a final question that sits beneath all the others. If ice ages, tides, winds, and fields are part of the natural background, what does it mean that human actions now rival some of those forces in their impact on climate? To understand that, and to see what choices still matter, we have to step back from individual cycles and look at how our fingerprints are beginning to appear in the very geological record we use to read Earth's past. When scientists read the history of Earth, they do not turn pages in a book. They drill, dig, and scrape.
Each ice core, each layer of mud on the seafloor, each band of growth in a tree is a thin slice of time. Tiny shells record the temperature and chemistry of ancient oceans. Pollen grains tell which plants flourished. Trapped bubbles of air hold the breath of long-gone atmospheres. For most of that record, humans are not there at all. Then, in the most recent layers, something strange appears. Signals that are sharp, global, and unlike anything in the older pages begin to show up all at once. One of the clearest signals is in the thin bubbles of air preserved in polar ice. For hundreds of thousands of years, carbon dioxide and methane rise and fall, within a band that matches the rhythm of ice ages and warm periods. The peaks and valleys line up with the slow changes in orbit and tilt we explored earlier. Then, in the topmost slices, the pattern breaks. Carbon dioxide shoots upward, climbing far beyond the range seen in those older cycles, and doing so in a geological instant. Methane does the same. If you plot those gases against time, the line does not gently curve. It bends sharply like a hockey stick lifted at one end. Other records tell matching stories. In ocean sediments, the chemistry of tiny shells reflects a rapid warming and acidification of surface waters. In tree rings and lake layers, shifts in temperature and precipitation unfold over decades instead of millennia.
Fossil fuel burning leaves subtle isotopic fingerprints that allow scientists to separate carbon from ancient coal and oil from carbon cycling through forests and soils. Taken together, the evidence says that a new forcing has been layered on top of the old cycles. It is not volcanic, it is not orbital, it is us. You can trace some of this transformation through energy. For most of human history, people burned wood, dung, and small amounts of charcoal. The energy flows were modest and mostly local. Then coal, oil, and gas were tapped in earnest. In a few centuries, the stored sunlight of hundreds of millions of years was turned back into heat and carbon dioxide. Machines multiplied the reach of human hands. Engines carried goods and people across continents and oceans.
That burst of activity built modern cities, medicines, and communications. It also thickened the blanket of greenhouse gases around the planet in a way that no natural cycle had done on such a short timescale. From the point of view of physics, the principle is simple. Greenhouse gases are transparent to most of the sun's incoming energy, but absorb and re-emit some of the infrared energy that Earth radiates back to space. Increase their concentration and less heat escapes. The planet warms until it finds a new balance where outgoing and incoming energy match again. That new balance can involve higher temperatures, different cloud patterns, and altered circulation. None of this is mysterious. It is the same logic that explains why a blanket keeps you warm, or why a glass greenhouse traps heat. What makes the current situation unusual is the speed and scale. Past natural releases of greenhouse gases, such as those from massive volcanic events, did warm the planet, sometimes with dramatic consequences for life. But those events often unfolded over many thousands of years. Species had time, though sometimes only barely, to shift ranges or evolve. Today, temperatures, sea levels, and rainfall patterns are changing measurably within a single lifetime. Creatures that migrate or bloom based on cues honed over many generations can no longer rely on those cues in the same way. The signs of this acceleration are now woven into everyday experience. Spring arrives earlier in many regions.
Glaciers that once fed rivers through dry summers have shrunk. Heat waves that used to be rare have become more frequent and more intense. Coastal storms ride on higher seas, pushing water farther inland. Coral reefs bleach under prolonged warmth. Forests that evolved under one range of temperature and moisture face new combinations of heat, drought, and pests. These are not isolated curiosities. They are symptoms of a system being pushed into a different state. At the same time, natural cycles have not stopped. The Pacific still swings between El Niño and La Niña. The polar vortex still gathers cold over the Arctic and sometimes lets it spill south. The lunar nodal cycle still waxes and wanes, shaping tides. The sun still pulses through its activity rhythm. What has changed is the background on which those cycles operate. A warmer ocean gives El Niño events more heat to redistribute. Thinner sea ice and altered snow cover change how the polar atmosphere responds to waves and disturbances. Higher average sea level turns a nodal high tide into a more frequent nuisance flood. You can think of it as turning up the volume of a song while the beat stays the same. Each drum hit, each bass line is still in its old place, but the impact on your ears and on the room is different. A storm that would have been manageable 50 years ago can now cause much greater damage because it rides on altered baselines. A drought that unfolds under a hotter sun can be more destructive to crops and ecosystems than a similar lack of rain under cooler conditions. There are other human fingerprints appearing in the geological and biological record. The spread of synthetic chemicals, from plastics to industrial compounds, leaves traces in sediments and in the tissues of animals. Radioactive isotopes from nuclear tests conducted in the mid-20th century form a near-global marker layer that future geologists will be able to see. Species are being moved around the world at a rate far beyond normal dispersal, altering ecosystems in ways that may endure for millions of years. Some researchers have suggested that these combined changes mark the beginning of a new geological epoch, one in which humans are a dominant force.
Whatever name we give it, the underlying idea is that our actions now belong on the same list of climate drivers as volcanoes, orbital cycles, and continental drift. For a long time, those drivers shaped the stage on which life unfolded while our species simply reacted. Now we have become stage builders too, sometimes without fully realizing it. This realization can feel overwhelming. It is tempting to frame the story as one of pure doom, an unstoppable slide toward catastrophe. It is just as tempting to deny the scale of our influence and insist that cycles alone will bring everything back to normal. Both responses are ways of avoiding a harder path, which is to accept that we are embedded in these cycles and capable of steering within them, but not of escaping their risks.
When you look closely, you find that not all future paths are the same. The amount of warming, the rate of sea level rise, the intensity of certain extremes all depend on choices about emissions, land use, and technology. If societies continue to burn fossil fuels at high rates, greenhouse gas concentrations will climb much higher, and the planet will move towards states not seen in many millions of years. If emissions are reduced quickly and deeply, the rise in temperature can be limited, and some of the most extreme outcomes avoided. The orbital cycles will still turn, but the track we follow through them will differ. You might ask whether it is already too late to matter, given how much change is already locked in.
The answer is that some effects, like a certain amount of sea level rise, are indeed now unavoidable because of past emissions and the slow response of ice sheets and oceans. But there is still a wide range between a world that warms a bit more and one that warms much more. Each fraction of a degree makes a difference to heat waves, to crop yields, to the survival of coral reefs, to the frequency of dangerous floods. Framed this way, the story is not about saving or losing everything. It is about how much risk we are willing to accept and distribute to future generations. There is also the question of how we live with the change that is already underway. Even in the best emission scenarios, some adaptation will be needed.
Coasts will have to decide where to defend, where to elevate, and where to retreat. Cities will redesign to cope with more heat, perhaps through shade, reflective surfaces, and green spaces that cool the air. Agriculture will adjust crop varieties and planting times, shifting where certain foods are grown. Water systems will be redesigned to handle both deeper droughts and more intense downpours. In each case, understanding the cycles we have explored helps avoid surprises. For example, planning for future tides without considering the lunar nodal cycle risks underestimating the frequency of flooding in certain decades. Designing power grids without accounting for solar storms and a changing magnetic environment leaves them more vulnerable.
Ignoring the possibility of altered jet stream patterns can make flood maps and heatwave preparedness plans less reliable. In that sense, paying attention to the old rhythms is a form of respect for how Earth works, even as we reshape parts of it. There is a quieter, more philosophical thread running through all of this. When you realise that your species can alter the composition of the atmosphere, shift the average temperature of the oceans, and leave a permanent mark in the rocks, you're forced to rethink what kind of creature you are. For most of history, people saw themselves as small in the face of nature. Storms, droughts, and ice ages were acts of fate.
Now we know that some of the storms and heat waves battering cities, some of the floods creeping into coastal streets, are amplified by human decisions. That knowledge can be paralysing if framed only as guilt. It can also be energising if framed as responsibility. You and I did not choose the starting conditions of the world we were born into. We inherited a set of technologies, expectations, and systems. But together, we influence how much further we push the climate system and how we respond to the changes already in motion. The cycles we have followed in this journey are not just background scenery, they are the rails on which our future runs. In the geological sense, Earth does not care what we decide. It has swung between warm and cold, wet and dry, with and without us.
Continents will keep wandering. Ice sheets will advance and retreat. Over long enough times, even today's sharp spike in greenhouse gases will flatten into a thin line in some ancient outcrop. What does care, in a very real way, are the living beings caught in the next few centuries of adjustment, including us and those who come after. So we arrive back at the question we posed near the beginning. Are we still moving with Earth's ancient rhythms, or have we stepped outside them entirely? The answer is a blend. The deep cycles of orbit, ocean, wind, magnetism and tide still set the framework. Within that framework, humans have become a new kind of force, capable of shifting the baseline quickly and of anticipating what those shifts will do.
We are both passengers on a slowly turning planet and mechanics with our hands on some of the controls. The open question is what we do with that position. Now that we can read the hidden clocks of Earth and see our own fingerprints on their faces, do we choose to keep cranking them faster? Or do we learn how to move in step with them? Do we treat knowledge of cycles as trivia, or as guidance for how to build cities, farms, and energy systems that can weather what is coming? The geological record will eventually record the answer in new layers of rock and ice. For now, it lives in the choices being made all around you, in countless quiet decisions about how we power our lives, where we build, and what we value. We began with the idea that weather feels like chaos, and that climate hides its order in long rhythms. We end with a different kind of mystery. In a world where we have become a geological force, can we find a way to live that respects those rhythms instead of fighting them? And if we can, what kind of future might that unlock for the species that now shapes the story of this planet?